The attribute ultimate in science refers to something that cannot be further improved because of fundamental limitations rooted in the laws of nature. The ultimate metrology for capturing electric field molecular fingerprints will have to cover the entire range of periodic intramolecular motions, including nuclear and electronic degrees of freedom. It needs to exhibit the highest sensitivity allowed by nature and to achieve the lowest noise fundamentally feasible. The highest possible sensitivity in measuring changes in molecular composition requires the advancement in both the excitation and the detection. The former must come in pulses with a duration comparable to the half cycle of the fastest motion to be initiated. These pulses maximize the amplitude of the electric field signals emitted. Such a sudden excitation also sets a window for zero background shortly after time zero for ideal signal detection, which is limited only by quantum noise. With these conditions met, the ultimate fingerprint detection will be realized by a field sampling technique that covers the entire bandwidth of nuclear and electronic motions and is able to detect each and every photon in the signal emanating from these intramolecular motions. Detecting the smallest changes in electric field fingerprints requires their noise to be minimized. Ultimate fingerprint metrology thus relies on ultra-fast excitation sources whose fluctuations are limited by the quantized nature of light, by the shot noise. In addition to nuclear vibrations, electronic migration may also contribute molecule-specific information to the electric field fingerprint. These motions are swifter, emitting electric fields more rapidly. Their resonant impulsive excitation calls for a correspondingly shorter sub-femtosecond near-infrared to ultraviolet excitation. The resultant electronic fingerprint is oscillating and decaying faster, offering over the spectral band of about 100 terahertz to 3 petahertz and other 1000 variables as potential carriers of molecule-specific information. The lowest frequency components of this electronic fingerprint probe the overall size and shape of a molecule. These signals may complement the information delivered by vibrational signals, which are dominated by next neighbor modes. Moreover, they unfold on time scales comparable to those of the fastest vibrations. The two types of motions may therefore affect each other depending on the relative timing of their initiations. Recording vibrational electronic fingerprints with combined infrared and near-infrared to ultraviolet excitation as a function of the delay between them yields two-dimensional vibronic molecular fingerprints. These provide us with an information-carrying capacity of many thousand variables. Ultimate electric field fingerprint metrology will optimally exploit this capacity by using shot noise limited and bandwidth limited multi-octave mid-infrared to far infrared and near-infrared to vacuum ultraviolet transients for impulsive excitation of periodic intramolecular motions, and terahertz to petahertz field sampling with single photon sensitivity for capturing the emitted molecular signals all the way from the infrared to the ultraviolet.